Hello everybody, and welcome back to another video on my channel. Today, we will be going back to integration and, as we were doing for the past couple of videos, talk about different techniques to solve integrals. Today's technique is especially powerful, and it's called U Substitution. Now, U Substitution basically means instead of having a variable be x, we do a smart and clever substitution that makes the integral easier and also changes the variable to something else. Most often for this, we use the variable u, although you can use any other variable and it will not really have an effect. U is just what we like to call a dummy variable. So without further ado, let's move on to actually explaining it. So let's say I have a function of f of some other function of g of x times something else, let's say h of x dx. Now, the thing is, integrating f, a function, of another function is very difficult to do without U substitution, as oftentimes they're not exactly the most elementary functions. Basically, they're not exactly, oh, this is insanely easy, now I understand how to do this. Especially since even if you can integrate this part over here, that doesn't mean you can integrate this part. So what we do is we have g of x is equal to u. But I kind of lied to you at the beginning. This h of x can't really be anything. It has to be some form of g dash of x times a number a, and this number a could be variable or it could not be. It really just depends on the integrals and the different techniques you're using to solving them. So what do we do now that we have g of x is equal to u? That's all good, but then what? Now here comes the trick. We differentiate both sides with respect to x. So we have g dash of x, or g prime of x, is equal to du by dx. Now, we have g prime of x, or g dash of x, which is exactly what we outlined over here. But what are we going to do with the dx? What are we going to do with the du? How is this all going to work? So now we're going to do something a little bizarre. We're going to multiply both sides by dx. Now normally this won't be possible, but as I explained in my differentiating series, or my differential calculus series on this channel, be sure to watch that before you watch this, as differentiation is very foundational for integration and many different techniques in integration. Differentials are basically just small, tiny steps in one direction or another, again and again and again. Now, you can also multiply by these differentials, and that's how the basis of the integral gets formed. So now, with that short detour done, now what we have is we have g dash of x dx is equal to du. So there we go. Now, since this h of x is g dash of x times a, we rewrite this integral as f of g of x times something times g dash of x dx. Now this becomes g dash of gx, this becomes du, and this becomes u. So now we have a times f of u du. Now integrating an elementary function in just one variable, this will be much, much easier, and we will get a times f of u, where capital F is the antiderivative of f of u, plus c, and then we substitute u back in for our answer, so we get a is equal to f of g of x, or capital F of g of x, plus c, and there's your answer. But, as you notice, a function within a function kind of looks like the chain rule. And this brings us to proving this equation. Now, I've shown you how it works, but now I'm going to show you how you can prove it, so you know that this is mathematically sound and has real logic behind it. So, let's get started on the proof. The basis behind this proof is we can prove that our integral of f of g of x times, in this case, we're just going to do g dash of x dx, where our a is equal to 1. And since we have a is equal to a constant, most of the time we can pull that out of the equation. And the times when a is a variable, it's often just another factor of u, and we do U substitution again, and it's not necessary to do that. So all we're covering right now is the base case, which is basically all you're gonna need to prove any other advanced forms of this proof. So, without further ado, let's also continue on this. So, now we have this is equal to f, or the antiderivative, of g of x plus c. So, what do? If we can prove that the derivative of the function on the right is equal to the function on the left, that means that this is true, as the integral is the opposite of the derivative. Thus, why it's also called the antiderivative. So, let's get to differentiating this using the chain rule. Now, big function f, or capital F, of g of x, when we differentiate this, how does the chain rule go? Well, the chain rule goes, if we have a function f of g of x, or in this case, let's have it a of b of x, so we don't get confused on our variables. This is equal to a prime b of x. So basically, we're taking b of x as x and just differentiating a multiplied by b prime of x. Now, there's a slight distinction. As I said earlier, this a prime will be the derivative of that function, and not when you're plugging in the other function into that function. I'm not sure if that makes sense, but it'll get cleared up when I explain this. And I also expect you to have a knowledge of derivatives right now. So, what we have is when we differentiate this, a prime, or the differentiation of capital F is lowercase f, so f, then we have of b of x, so g of x, and then multiplied by g prime of x. And c, since it's a constant, its derivative is 0. So, as you can see over here, this derivative matches up with the chain rule. And now that I showed you this, you understand what I mean by a prime of b of x. So if I had, let's say, e to the power of x squared, and I differentiated this, I would have e to the power of x squared. So it's like I'm differentiating just e to the x and then resubstituting it back in. So sort of like a mini U substitution, but for derivatives. And then I multiply by the derivative of the function, just for a refresher on the chain rule. So now that I've shown you how U substitution works and I've proven it to you, let's move on to solve 2 examples that will get you introduced to applying this concept in actual integral problems. Although one more thing, before we start solving those problems, I need to explain what this means for a definite integral. And I'm so sorry I missed this earlier, but I'm explaining it right now. So, what does happen to a definite integral? Well, if I have the integral of a to b of f of g of x times g prime of x dx, and I take g of x is equal to u and do my u substitution, I'll get the integral of f of u du. So now these boundaries have to be adjusted for our new variable u. And since in the previous equation these boundaries are just limits for x, now they'll be limits for u or g of x. So we have to substitute these x values into the equation in order to get our u values, as that is what is the new limiting factor. So it'll just become g of a and g of b. Hope that clarified stuff up for you. Sorry that I came after I said I was going to do the problem, but now let's really move on to our problems. Well, over here we have our first problem. The integral of x squared multiplied by e to the x to the third, or just e to the x cubed, and then dx. So the first thing to know for is when we're substituting for u, always look for stuff that's a compound function. Basically a function inside another function. Like, let's look over here at e to the x cubed. This looks like e to the x, but x is x cubed instead, and that's two different functions in one term. So that's a good place to pull our u from. So how will we exactly pull our u? Well, our best bet, since we have x squared over here, and we know that the derivative of e to the x is just e to the x, let's take x cubed as our u. So x cubed is equal to u, and du is equal to 3x squared dx. Now, I just skipped over the part where we went du by dx and then multiplied both sides by dx. You can also just take it like this, as again, you're keeping the differentials into account and accounting for the slope of the graph, which is what the derivative is. So, now that we have our two terms, we realized that we don't have a 3 in this equation. So, what do? We accommodate for what we have. So if we just quickly rewrite this as e to the x cubed multiplied by x squared dx, and over here we see we have x squared dx, let's isolate that. So x squared dx is equal to du by 3. And since 1 by 3 is a constant, it doesn't really affect our problem solving process at all. So we can substitute x cubed for u, and we can have 1 by 3 on the outside. Then we have e to the power of u du. Now integrating that from our last video, which you should also definitely watch, we get 1 by 3rd e to the u plus c, and substituting u, we get 1 by 3 e to the x cubed plus c. And there we go. That is the answer to our first problem. Over here, we have our second problem. 2 multiplied by the integral from 1 to 2 of x times 2 to the power of x squared dx. Now this is a definite integral, so we will also have to use techniques for solving the definite integral in this problem. But it shouldn't be too hard. Now, the first thing, as I said in my last problem also, is notice for functions that look like a compound function, or a function with another function. And a good point to look at that is where you have multiple powers, or you have trig functions and other things inside those trig functions. But we're not integrating trig functions yet, as in order to prove some of them, we need this U substitution. So that will come very soon. But what's important right now is we notice that this 2 to the x squared is a power tower and has multiple powers on top of each other. So now, and as we said earlier, we should look at what's on top, and since there's x, we should probably take a polynomial, and the only polynomial is x squared. So our u is equal to x squared. Now, differentiating gives us du is equal to 2x dx. Now, as you can see, we don't have the 2x, but we have this 2 on the outside. And by integral properties, we can move it on the inside. So we're left with this equation. And now we can substitute everything in. But one last thing. Remember, as I said earlier, our limits also have to change because now we're differentiating with respect to u, not with respect to x. So now that we have u is equal to x squared, what we do is we plug in these x values. So u1, which is the lower value, will be 1, and u2, which is the upper value, will be 4, since 4 is 2 squared. So we'll have that from 1 to 4, and then we substitute 2 to the power of u du. Now, by the formula discussed in our last video, which was also proven, this integral 2 to the u becomes 2 to the u divided by the natural logarithm of 2, now from 1 to 4. So let's put 1 by ln 2 on the outside and substitute 1 and 4 for this. So 2 to the power of 4 minus 2 to the power of 1. Now this becomes 16 minus 2, which is 14. So we get 14 divided by the natural logarithm of 2, and that is our final answer for this problem. I hope you enjoyed looking at these problems and solutions and me just explaining this topic to you. If you enjoyed this video a lot, please make sure to like, subscribe, and hit that notification button. But above all of that, thank you so much for watching this video, especially if you're watched until the end, as it really means a ton to me and for this channel. So, once again, please make sure to comment down below if you have any suggestions or anything else that you want to say that's encouraging, kind. Just don't try and be mean to anyone or demoralizing, as that's not a good thing to do. But besides that, enjoy, have fun, learn some new math, and thank you so much for watching. See you in the next one, and bye-bye.